Welcome back, everyone. Our next speaker is João Paulo Figueiredo, who is going to talk about regular foliations on rationally connected manifolds.
Can everybody hear me? Okay, thank you, Thiago. Thank you, the organizers, for inviting me. Today I'm going to talk about a subject I worked in my thesis with Carolina, and it's about regular foliations on rationally connected manifolds. So I will present to you the definition of foliations, give you some motivations, and basically I'll talk about one problem I worked. So to start, I work everything I'm going to talk here is over the complex numbers, and the varieties are complex varieties, and so on. And holomorphic foliations, you already saw the definition, but let me give you again. They come from the study of holomorphic flows, which are defined by the solutions of complex differential equations, which is equivalent to holomorphic flows defined by complex vector fields. Okay? Okay. Is it okay? Okay. So, for instance, if you consider an open set on C2, you can define a complex vector field here, holomorphic, and by the theorem of existence and uniqueness of solutions of ordinary differential equations, you know that through each point there is a curve whose tangent is given by the vector corresponding to this point. So you decompose the open set into a union of curves, and this is a prototype for a foliation, in this case, by curves. Okay? So as you know, it's interesting to study these objects. They have a lot of applications, and it's interesting to study the properties of these curves, for instance. For instance, you can ask whether these curves are algebraic curves, or whether these curves are dense, and so on. Okay? And for instance, so this is a local picture, and you can also consider a global picture by gluing these local objects together and form a global object in a projective variety, for example. So you can consider, here I'm drawing a real manifold, but just for illustration, so you can see it. This is a two-dimensional torus, and this is a foliation by curves in this torus. So in this example, the curves are disks, topological disks. But it can also happen that the leaves, the curves, are dense in the torus. So it's a good question to ask for conditions which can, for conditions to distinguish between the two cases, whether the curves are disks or are dense in the torus. So this is one example of a way we can study foliations. So we can try to generalize these objects to consider, instead of decomposing the manifold into a union of curves, we can easily think of a decomposition into a union of higher dimensional manifolds. So a general foliation. So in this case, for one-dimensional curves, you can see that the curves are actually have these tangents. So what we have here is a distribution, holomorphic distribution of dimension 1. So it's a subsheaf of TC2 of rank 1. So in order to generalize, it's enough to consider a distribution of higher dimension. So a foliation will be defined by a distribution. So on a manifold will be a distribution of rank 1, of rank R. In other words, to each point, instead of assigning a line of dimension 1, we assign a plane of dimension R. And we only ask that this distribution is integrable. In other words, through each point, there is a manifold which is tangent to the plane in this point. So a foliation will be a decomposition of a manifold into a union of immersed submanifolds of dimension R, which are tangent to a distribution of rank R. Okay? So one example is this red foliation. This is a real foliation of dimension 2, rank 2, in solid torus. Okay, so these are very interesting objects, as you saw, and it's interesting to try to classify them. And several mathematicians worked on this topic, and today the problem I'll tell you about, it's in the intersection of the theory of foliations and birational geometry, complex birational geometry. Okay? So to start, I will motivate the problem with a result by Marco Brunella, which classifies foliations on rational surfaces. So let S be a rational surface, so a complex rational surface, and consider a foliation over S. So my question is, how does it look like? How does this foliation look like? Okay? So the result by Brunella shows that every foliation, the way foliation of rank 1, the way I define it here, is actually induced by a fibration with rational fibers. So that you consider a fibration, a smooth fibration, in the leaves, and the fibers of this fibration will be the leaves of the foliation. Okay? So a sketch of this proof is the following. For instance, if S is a P1 bundle over P1, so this is a usable surface, you can compare the foliation with this fibration. So you have two cases. The first case is the foliation is induced by this fibration. So in this case, we have the result that the foliation is actually induced by the fibration. The other case is the case where the general leaf is not contracted to a point. So what he shows is actually that since the foliation is regular, every leaf is everywhere transversal to the fibers of the fibration. So in this case, the leaves are actually étale covers of P1, in other words, are P1. Okay? So in this case, the leaf is P1. So every leaf is P1. So the foliation is induced by a fibration with fibers P1. Okay? And this is what he shows. In the general case, every rational surface is obtained by a Hilbert surface by a sequence of blow-ups, except P2. And we can make a calculation and reduce the general case to the case of Hilbert surface. I won't show the details here. Okay? So what he actually shows, to summarize, is that every foliation on a rational surface is actually induced by a fibration with leaves, with rational leaves. And this is a very nice result because it classifies the regular foliations on every rational surface. So it's natural to think of a generalization of this result to higher dimensions. So a way to generalize rational surface to higher dimensions is to consider rationally connected manifolds. So a manifold, projective manifold X, is rationally connected if you consider any 2 points, you can always find a rational curve connecting these 2 points. Okay? So you can see that rational surfaces are rationally connected. And you consider this class of manifolds in higher dimensions. So a conjecture of which generalizes these results by Brunet is the following conjecture made by Frédéric Touzé. If you consider a rationally connected manifold and a regular foliation on X, then this foliation will also be induced by a smooth morphism with rationally connected fibers. Okay? So one instance of this conjecture are the Wick-Fano manifolds. So Wick-Fano manifolds are a generalization of Fano manifolds, are manifolds whose anticanonical bundle is Neff and big, and it's proved by Druel that the conjecture holds for Wick-Fano manifolds. In other words, he proves that any regular foliation on Wick-Fano manifolds are induced by smooth morphisms. And his method, just to say a few words, is to consider the linear system defined by the determinant of the normal bundle of the foliation and show that this linear system actually defines a fibration by Wick-Fano manifolds, which defines the foliation. Okay? So, my result is a generalization of the Druel's result. I show the conjecture for manifolds which are rationally connected and have Neff anticanonical bundle. If you remember, Wick-Fano manifolds, the anticanonical bundle is Neff and big. So I remove the condition big and keep the Neff condition. And I show the result for, in the case, the dimension is 3, the dimension of the manifold is 3, and the codimension of the foliation is 1. So this is the result. So it proves the Touzé's conjecture in the case of 3-dimensional manifolds and codimension 1 regular foliations with these conditions. I won't tell you the details of the proof, since I don't have time, and other case, but I leave you the references. So if you want to know a little bit more about birational geometry of foliations, I recommend the book by Brunella. And then you have other references you can look. Thank you.